Welcome to this course of chemical crystallography. In this lecture, I am going to discuss the solutions to the problems given in the assignment 4. So, the first problem that is given here is based on a structure of copper oxide. So, the question is the unit cell of binary compound of copper and oxygen is shown here. Given this image and the ionic radii of copper as 0.74 angstrom and oxide as 1.26 angstrom, determine the empirical formula of this compound. So, what you could see here is that the unit cell that is drawn has oxygens at corner positions. So, 8 corners have 8 oxygens. And each oxygen is 1/8 contributing to the cube. So, you have 8 O2- ions at corners. So, they contribute 1/8 each. So, 8 into 1/8 is equal to 1, plus you have 1 oxygen at the center. So, you have oxide ions at corners plus 1 O2- at half, which means you have 1 plus 1, 2 O2- ions in the unit cell, and it is clearly visible that there are 4 copper ions, Cu2 plus ions or Cu plus ions, Cu plus ions. So, you have 4 Cu plus ions at alternate one-fourth type of sites, which means if it is there at 1/4, it is not there at 1/4, half, 1/4, things like that. So, you have 4 full copper ions and 2 oxide ions. So, it corresponds to a formula like Cu4O2, which is equivalent to Cu2O. So, this is the empirical formula of the compound that is shown here in the structure. Now, determine the coordination number of copper and oxygen. If we look at the central oxygen, we see that there are 4 coppers nearby, and this is true for all oxygens if you grow the lattice in all 3 directions. So, coordination number for oxygen is 4. Now, if you look at the structure more carefully, what we see is for every copper you have only 2 oxides nearby. So, the coordination number for copper is just 2. Now, the next question is estimate the length of the edges of the cubic unit cell. So, what we see here is that this particular structure has a packing along the diagonal in such a way that you have R anion, this point is 2R cation, this part is again 2R anion, this part is 2R cation, and this is again R anion. So, if we add all that is the diagonal, is nothing but R0 plus 2RC, R cation plus R oxygen plus R copper plus 2R oxygen plus 2R copper plus R oxygen, which is equivalent to 4 times RO plus RCU. and this is nothing but equal to the diagonal, which is root 3a. So now the values for RO and RC are given. RO is 1.26 angstrom and RCU is 0.74 angstrom. So which means A equal to 4 into 2 angstrom by root 3, which is equal to 4.6188 angstroms, the edge length. So when we try to estimate the density of this compound, what we need is the density D is equal to mass by volume. What is this mass? Mass of all the atoms inside the lattice. All atoms inside the unit cell divided by the volume of the unit cell, which means we are talking about 2 into mass of oxygen atom plus 4 into mass of copper atom divided by the V cell. So we can write it as 2 into 16, which is atomic weight of oxygen, plus 4 into 63.55, which is atomic weight of copper. This is the molar mass. So mass of one atom is divided by Avogadro number divided by the total volume of the unit cell, which is 4.6188 into 10 to the power minus 8 centimeter whole cube. So if you calculate this number, this density should turn out to be 4.8 gram. This is gram per cc, or 4.8 gram per centimeter cube. The question number 2 is based on the formula that one can derive from simple Bragg's law for a cubic cell, that 1 by d square is equal to h square plus k square plus l square by s square. For 111 plane, we write 1 by d111 square is equal to 1 square plus 1 square plus 1 square by a square, and this d111 is given. So we can write a square equal to 3 into d111 square, or simply a equal to root 3 d111. So that means it is equal to root 3 into 325.6 picometer is equal to 563.9 picometer. So now we write the same equation for D333. 1 by D333 square is equal to 3 square plus 3 square plus 3 square by a square, or D333 is equal to a square by 27 square root, which means it is a by root 27, which is nothing but 108.5 picometer. The question number 3 says that it is a simple cubic crystal, which is important information here. To get the values for D101 and D111, we should be able to write the Bragg's law for these two reflections. N lambda is equal to 2D101 sin theta 101 is equal to 2D111 sin theta 111. So that means if we want to calculate the value of sin theta 101 by sin theta 111, we need to calculate the ratio D111 by D101. So how do we do that? We write again 1 by D111 square is equal to 1 square plus 1 square plus 1 square divided by a square, or D111 is nothing but a by root 3, and similarly 1 by D101 square is equal to 1 square plus 0 square plus 1 square by a square, or D101 is nothing but a by root 2. So if I try to do D111 by D101 is nothing but a by root 3 divided by a by root 2. So it is equal to root 2 by root 3, which is equal to 0.817. So this is the ratio of sin theta 1 by sin theta 2 for this particular crystal. The fourth problem here that has the question on systematic absence. The question is, for a given set of crystallographic data, if the reflections having Miller indices 011, 029, 051, 027, 005, 013, etc. are absent, identify the symmetry element present. On observing these reflections, you can clearly see that the 0KL set of reflections are absent when L is odd. You see, 1, 9, 1, 7, 5, 3, with all values of L being odd, are absent. This means that it is a glide plane, because in case of screw axis, two indices are 0, whether it is H00 or 0K0 or 00L represent 2-1 screw, but here it is 0KL, that means it is a kind of mirror, which is a glide, and the absent condition says that L is odd, which means it is a C glide perpendicular to X. So this systematic absence condition indicates a C glide perpendicular to X. So you should be able to then identify these systematic absence conditions, given if the condition, the systematic, you should be able to analyze the systematic absence conditions and then come to a conclusion that what kind of symmetry element is present in the lattice.